Hello, my name is Mark Summers. I'm a graduate student here in the Ingram School of Engineering, working on my master's degree in manufacturing and mechanical specialization. And my project is working with atmospheric water generation. So we're trying to extract liquid water from the water vapor that's in the air around us to be able to use for drinking and agricultural purposes for areas of the world that don't have access to readily available access to water. So let's talk about project, and so let's move over. Let's look at some pictures here. This is the original test platform that I designed. We're using these off-the-shelf Peltier devices that create a temperature difference across a ceramic material, and you supply a DC voltage and you're able to get one side cold, one side hot. The idea is the cold side is where the water is going to condense out, and the hot side we need to keep cool to keep the temperature delta T down to a reasonable amount. So these are commercial items we bought, designed and built a test platform to mount some of these. We ended up testing 4 of them at a time, and we got some preliminary results, but the water collection rate was very, very low due to the small size of the condensation plate. So what we did was went to a larger version on the second go around, and we wanted to investigate, which is the main purpose of this talk today, is investigating multiple heat transfer mechanisms to be able to cool the hot side of the Peltier device in a manner that'll help optimize the operation of the system. So if we look, this is the larger assembly CAD model. These condensation plates are 8.5 by 8.5 inches. There's 4 of them eventually, and we have different configurations for different numbers of Peltier devices. So there's 4, 3, 2, and 1. Each one of them supplied with a fan to cool these heat sinks, and we've also added another heat transfer mechanism, which is using heat pipes, and it's a very efficient way to transfer heat because it uses a phase change mechanism. It's a vacuum sealed copper pipe that has some wicking material in it and distilled water, and it acts like a condenser and a evaporator side, and the water cycles through there and extracts heat in a mechanism that we didn't use on the first test platform. So if you look over here at the assembly, we've got some large fans back here that blow through these ducts, depending on if it's however many Peltier devices we have, and we're optimizing those as well. And you can see a cutaway here without these tubes. You can see those heat sinks and these heat pipes. So through that testing, we've also done some analysis using computational fluid dynamics program we have, and we can run simulations showing the airflow through those ducts and optimizing the design such that we don't have to build multiple iterations of this. We do testing and use the results from the finite element analysis to allow us to optimize the shape of the duct, the amount of airflow, and then decide on an actual configuration to build. And we correlate the data between the testing and the actual test system over here on my shelf where we do the testing. So in addition to the simulation, we've also got some thermal camera imaging capabilities, and so I can run time studies to see how quickly, this is one of these 8.5 by 8.5 inch condensation plates. You can obviously see behind that where those Peltier devices are, the thermoelectric coolers that cool that condensation plate. So the optimization here is figuring out what configuration, geometric configuration of those Peltier devices to use so that we get a nice cold temperature across the plate without expending too much energy. So depending on the number of Peltier devices and the amount of current we flow through there, we're trying to optimize to get the coefficient of performance of these Peltier devices down to a level that is optimized so that we get the most water for the least amount of energy expended. So that's a brief summary of the project, and we'll go into more details during the actual conference. So thanks for your time. Have a good day.